Before we stick any numbers in, I want to point out that I am sure you have a very good qualitative understanding of this result, tau equals RF sine theta, because I am sure that just about every day you use torque. For example, every time you open a door, you use torque to rotate that door. So let's think about what you do every time you open a door. Let's imagine that the origin of our door is the hinge. That's the point about which the door is rotating. Now let's imagine you want to open a door very quickly. Do you open the door and apply a very light force? Or do you apply a strong force, assuming you want to open the door quickly? Well, you know if you want to open a door quickly, you pull on it hard because that will open the door faster. The larger F, the greater the torque. Now let's imagine I'm going to close this door. I'm going to push on it. Where do I push on it? Do I push on it over here, far from the hinge, or do I push on it over here, close to the hinge? Well, if you were going to close the door, where would you push it? You would push on it over here, far from the hinge, because you know it's easier to close the door if you push on it far from the hinge with a greater distance r. Remember, r is the distance from the origin. The farther you push on the door from the hinge, the greater the torque, the easier it will be to close the door. Now one more thing, in what direction do you push on the door? If I'm going to push on this door, do I push on it in this direction, perpendicular to the door? Or do I push on it this way, toward the hinge? Or do I pull on it this way, away from the hinge? No, if I want to close the door, I know I'm going to push on it in a direction that's perpendicular to the door, and that's going to close the door in the easiest way. By pushing on it in a direction that's at what angle? 90 degrees to the r vector, so that your force is perpendicular to r. We have a very good qualitative understanding of all of those terms. The greater the force, the greater the torque. The greater r, the greater the torque. And we want sine theta to be large. In other words, we want theta to be 90 degrees. That's a very, very good qualitative understanding. The only thing is, quantitatively, it's just a little bit more difficult. It might seem a little more complicated, but keep in mind that qualitatively you already have a very, very good understanding of what torque means. Okay, now let's stick some numbers in there. Let's imagine that we have a seesaw. I had a number of semesters ago, I had a student who actually told me they didn't know what a seesaw was. So just think of a seesaw as a board that is balanced at the center and can go up and down. And children like to, or some adults do I guess, like to get on, and they can go up and down on the two ends. Let's imagine our seesaw is 3 meters long, and we'll assume that the board itself is massless. In other words, at least we'll assume that the mass of the board is much, much less than these two children that will be sitting on it, so we don't have to worry about the mass of the board for the moment. The seesaw is 3 meters long. It is balanced at the center. On one end of the seesaw, we have a child with a mass of 50 kilograms. And another child with a mass of 75 kilograms wants to get on the other side and wants to sit in a place so that the seesaw balances. If the child on this end were to sit at, say, at the very end, the seesaw would just go down like this, and the other child would go up in the air, and it wouldn't balance. Let's see if we can figure out where on the seesaw should the child sit so that the seesaw will balance. We will just put the child, let's say, here, and at some distance d from the center. And so the question is, what is this value of d? Where will this child sit on this side so as to balance the 50 kilogram child on the other side? Very good. Let's draw in the forces. What forces are acting on the meter stick? Not the meter stick, on the seesaw. We've got 3 forces. We have the weight of this child. We need to draw that force in. What we're going to do is we're going to draw a free body diagram for the seesaw, but we've got an extra complication. Now that we're looking at rotational dynamics, we cannot just draw in the force or forces anywhere we want. We have to draw the forces in at the point where it acts, where each one acts. Because the distance from that point to the origin is going to be important. It's going to help us determine how much torque that force is applying. So we've got to be a little bit more careful now with our free body diagram. The weight of this child, where does that force act on the seesaw? Where the child is sitting. So we'll draw this force acting over here. And what's the direction of the force? The weight by the child is acting straight down. So this is the weight of the 50 kilogram child. What's the magnitude of that force? Well, that weight we know will be mg, 50 kilograms times 9.8. What is that? 490 newtons. So there's the weight of the 50 kilogram child. What else is acting on the seesaw? Well, the weight of the 75 kilogram child. Where does that force act? That force will act wherever that child is sitting. So we'll apply that force over here. And what's the direction of that force? It will be, again, straight down. And what's the magnitude of that force? It is mg, 75 times 9.8, which is 735 newtons. So this one, this weight, call this W2 and W1, 735 newtons. Anything else? Any other forces? There has to be another force acting on the seesaw. If the only forces we have are both down, the seesaw would accelerate downward. It would just fall down. There has to be a force acting in an upward direction. Where is that force coming from? It's coming from the support. The support that the seesaw is balancing on. There has to be an upward force acting on the seesaw, pushing it in that direction upward to keep it from falling down. So we know we must have some force over here acting up. We'll call this F sub S for the support force. Very good. Those are the only forces. We could add in a weight for the seesaw. The gravity itself could be acting on the seesaw, but we'll hold off on that. We'll talk about how weights act on objects, the object's weight, later on. There we go. Now let's take a look at the torques. What torques are acting on the seesaw? In order to determine torques, we have to have an origin. Because remember, what's torque? Torque is RF sine theta. In order to figure out what R is and theta, we have to have an origin. Where shall we put our origin? Let me suggest that we put the origin at the center of the seesaw right there. We are free to choose our origin anywhere we want, just like we have always been. Anytime we want to choose a coordinate system, we can choose our coordinate system anywhere we want. We can put our origin any way we want. We can choose the direction of our X and Y axes anywhere we want. In this case, we are again free to choose that, but let me just make a suggestion that we put it here, and we'll see why that actually is going to make it a little bit easier for us. There we go. That's our origin. We've got three forces. We need to figure out three torques. And then, for the stick to be stationary, we're going to use the idea that the total torque acting on the stick has to be zero. And I mentioned this before, if an object is not rotating, the net torque acting on it has to be zero. So what do we know? We know that the net torque acting on the object must be zero. So let's figure out what is the torque for each force. We'll call this tau 1, tau 2, and tau 3. And the total torque must be zero. So what is the torque from the first child, the 50 kilogram child? We'll call that tau 1. Tau 1. Well, what is torque? Torque is RF sine theta. What is R? We have to add up the torques. We need to calculate each torque separately and then add up the torques. So we have to figure out torque 1, and that'll be, say, R1 F1 sine theta 1, for example. So what is R for the first torque? Remember, R is the distance from the origin to the force. Here's the force. Where's the origin? The origin is over here at the center of the seesaw. What is this distance? Well, if the seesaw is 3 meters long and this is at the center, that's going to be half that distance, or 1.50 meters. So R for the first force, first torque, is 1.50 meters. What is F for the first force? 490 newtons. Sine, and what is theta for the first force? Well, here is R. R is the vector that goes from the origin to the point where the force is applied. That's R, the length of which is 1.5 meters. Theta is then the angle between R and F. How do we find the angle between vectors? Put them tail to tail. So here's R, here's F. Move it tail to tail. The angle between them is 90 degrees. Sine 90 degrees. Very good. One more thing we have to think about, and that is, how do we distinguish torques that would tend to rotate an object clockwise versus torques that tend to rotate objects counterclockwise? Well, we're going to adopt a standard orientation, and that is that torques that tend to rotate objects counterclockwise, we'll call those positive torques. This is just like when we were measuring angles in rotational kinematics. Remember, angles that were counterclockwise were positive, angles, velocities, angular accelerations that were counterclockwise, those were all positive. Angular velocities, angular accelerations that were clockwise, those were negative. We're going to use the same orientation for torques. So clockwise torques, in other words, torques that would tend to rotate the object in a counterclockwise direction, we'll think of those as positive torques. Torques that tend to rotate objects in clockwise directions, we'll think of those as negative torques. There's another way of defining directions in terms of torques, and that gets back to that order of RF sine theta, but we're not going to worry about that at the moment. That uses something that's called the right-hand rule, and we won't worry about that right now. For now, we'll just think about torques as being clockwise or counterclockwise. Now in this case, for this torque, is this a clockwise or a counterclockwise torque? Well, think about the seesaw. This force is pushing down this way, which would tend to rotate the seesaw in a counterclockwise direction. Another way of thinking about this is, if you were to continue this force around the origin, so down this way and go around the origin, that would go around the origin in a counterclockwise direction. So this is a positive torque. So this one is a positive torque. Very good. We multiply this out, and what do we get? We get 735 Newton meters. Positive. Very good. Let's try the second one, torque 2. What is the torque due to the second child? Well, what is R? Again, R is the vector that goes from the origin to the point where the force is applied. The force is being applied where the child is sitting. So that is our vector R, R2. What's the length of R2? Well, that's this distance D. That's what we're looking for. So R for the second child is D. Times F. What is F for the second force? That would be the weight of the child, 735 newtons. Times sine theta. And what is theta for the second child? Well, here we have R, here we have F. Again, put them tail to tail. What is the angle between them? Again, 90 degrees. So sine 90 degrees. Is this a positive or a negative torque? You think about it for a second. Is this force tending to rotate the stick clockwise or the seesaw, clockwise or counterclockwise? In this case, here, we're pushing down this way. That rotates the stick clockwise. Or continue this force around the origin, and it's going in a clockwise direction, meaning it is a negative torque. So we put a negative sign over here. Multiplying this out, again, sine of 90 is 1, we get negative 735 newtons times d. Very good. Now, what about the third one, the support force? What is the torque due to the support force? I'll call that tau sub s. What is R for the support force? I'll let you think about this just for a second. Turn off the video if you want and think about it. What is R for the support force? This is a very, very important point. It is 0. Any time we have a force that acts at the origin, it creates 0 torque. Like pushing a door at the hinge. This creates 0 torque. If we were to draw a vector from the origin to the point where the force is applied at the origin. So the vector r would have 0 length. So r is 0. The torque due to the support force is 0. This is an important point to keep in mind. Anytime a force acts at the origin, it creates 0 torque. Because we are free to choose the origin anywhere we want, sometimes it's very useful to choose the origin at a point where a force or forces act so as to remove those torques from the problem. We don't have to worry about the torque created by those forces if we put the origin at the point where that force or forces are acting. Excellent. So there we go. There are our 3 torques. What we know is the net torque must be 0. Excuse me. So let's add these up. What do we have? The net torque must be our first torque, 735 Newton meters, plus the second torque, which is minus 735 newtons times d, plus the third torque, which is 0, must equal our total net torque, which is 0. Bringing the 735 newtons d to the other side, divide by 735 newtons, and what do we have? We have d equals 735 newton meters divided by 735 newtons, leaving us with d equals 1 meter. Very good. What is this telling us? This child must sit at a distance of 1 meter from the center. In other words, 0.5 meters from the end of the seesaw to balance the first child. Very good. Excellent. Let's just recap. How did we solve this problem? We drew a free body diagram with all of the forces acting on our object, the object being the seesaw in this case. Why did we pick the seesaw? The seesaw was the object that was not rotating. It's the object in the problem that we knew was not rotating or wasn't supposed to be rotating. That's the whole point, to put the child on the seesaw so that they would balance. The object in the problem that was not rotating, which then must have 0 net torque acting on it. We then looked at the forces acting on the seesaw, drawing a free body diagram, making sure that not only did we draw the forces on the diagram, but we were very, very careful about where on the object those forces were acting. The first force acted at this end, the second force acted wherever this child was going to be sitting, and the third force acted at the support force. And then we determined the torque due to each force, and the net torque was then the sum of those forces, and we knew the net torque had to be 0. And then from there, we solved for what we were looking for. Very good. Let's try another one.